looking at applying our integrals to kinematics, and this is very similar to what we've done before. With derivatives, you move from displacement to velocity to acceleration. And so now with integrals, we are able to move backwards. Right? So in derivatives, we took displacement, we took the derivative, we got velocity. We took the derivative of velocity, we got acceleration. But what happens if you started with acceleration? Well, you could integrate and get back to velocity. And if you had an initial condition, it's like a solving for C kind of question, you could find the actual velocity equation. And if you had additional information about displacement and working backwards, you could solve the actual displacement formula. So in this question, we have an equation for our acceleration. Our acceleration is t plus 1. We want to find the velocity and the displacement formulas, and we're given some information. We're given when time is 0, we have an initial velocity of 8 and an initial displacement of 0. So if we have our acceleration and we're thinking, we can work our way backwards, integrate first to get our velocity. This is relatively easy integral. Add 1 to the exponent, divide by it. So t squared divided by 2 plus t plus c. And so since we're doing an indefinite integral, we have to do the plus c, but our initial at time equals 0, our initial condition said that velocity was 8, so we can plug in 8 for the velocity, 0 for time, and find out that c has to be 8. And so now we have an exact equation for our velocity. And we can do this again and work backwards and find x. Now notice in this question, you used c plus c when you integrated to find velocity. You might be tempted to do plus c again, but in the same question, we can't use the same variable twice. So sometimes I like to use D because it comes right after C. In this case, we use K. It doesn't matter what letter you use. Just don't use T. But you do need to, in a question where you're integrating twice, if you're doing the integral twice and moving up twice, you've used plus C once. You can't use plus C again. You have to introduce a new variable. But here too, we know that when time is 0, S is 0. So this would solve for K, and we get our displacement equation as well. So as far as recognizing questions go, whenever you're moving up, you know that you need to integrate. Whenever you integrate, you're going to have a plus C. If you're given another piece of exact information, that usually means you'll be able to solve for C. So I would recognize this question and go, oh, this is a solving, I call them solving for C questions, because you've got enough information that when you integrate, you can actually solve for C. This time in class, we're starting with the velocity equation. So if you want to find the acceleration, then you're going to need to find the derivative. So acceleration is the derivative of velocity. And you just get negative 10 meters per second squared. So this is the derivative. If I want to get back to displacement, now I'm going to need to integrate, okay? And they give us an initial condition. Whenever you see initial, that's telling you that's when time is equal to 0. So this is a solving for C question. We're going to integrate first. Relatively easy integral to figure out. Have our plus C. Now put in our initial condition, and we can solve that C is 40. Then we can write our final equation. All right, so try this one on your own. I'll put up the answer in a bit. Most people are done A and B, so I can do a quick check. If the particle is at rest, the velocity is 0. You need to take your velocity equation and set it equal to 0. I'm not sure if this is something that you want to highlight. And then factoring that and solving it gives you 2 answers, 3 seconds and 1 second. And then you plug those back into your displacement equation to find your actual displacement. All right, we have seen this already, but we're going to really think about it, that distance and displacement are different things. If I throw a ball up in the air and catch it at exactly the same place, its displacement is 0, but it has traveled a distance. Okay? And I think this is the key thing for me in real life, why I don't like going for a run. Because I leave my front door, I go for a run, I get back to my front door, and logically I think to myself, I could have got here a lot quicker if I didn't leave. Right? If I need to get somewhere, then I have no problem walking or running. Running if I'm late, walking if I have lots of time. Then it seems like there's a purpose, and my displacement is the same as my distance usually because I'm going somewhere. But if I go for a run and come exactly back to where I started to, now I'm like in my head I try to convince myself, this is good. This is going to get me ready for soccer season. But man, I could have got here a lot sooner if I wouldn't have left. Now, when we think about integrals, and we think about accumulation of change, when we integrate a velocity function, the area under the curve is an accumulation of change. It is our displacement. But sometimes that displacement is negative, and sometimes that's positive. When you go for a run, your displacement starts off positive because you're getting farther away from your house, but then eventually you start going back towards your house, and then your displacement is getting accumulated as a negative value until you're back home and it evens out. So If I want to find out how far I ran, that would be a distance. And distance is just an absolute value of your integral. If you took this negative part and you flipped it above and made it positive, now adding up these three positive sections will give you your distance. And this is something that can be very useful on our calculators to be able to do. Because we can integrate on our calculators, but anytime we do a definite integral between two values, it will calculate the negative and the positive and cancel everything out. So one of the things that we're going to do is, hey, if I took this initial velocity function and I took the absolute value of it, that would flip parts that were negative above the x-axis. And now all of my areas are positive. So displacement is just the regular integral between two values. Distance, this is the complicated way of doing it. You could say, well, I could figure out which sections are positive and which sections are negative, calculate them separately, then the negative answer I could make positive at the end and get a final answer. But if I'm allowed to use my calculator, it is way faster just to take the absolute value at the beginning and calculate it that way. So we'll look at some examples this way. We've got our velocity equation. If we want to find the object's displacement, so here is displacement, not worry about positives or negatives, we can just integrate. I can just do the integral from 0 to 3 pi over 4. Now, it's not bad if you're integrating and you kept the 2 out in front and remembered because of the chain rule you'd have to divide by 2. The sign changes to positive because the derivative of cos is negative sign. So the antiderivative of negative sign is positive cos. We're evaluating this from 3 pi over 4, or from 0 to 3 pi over 4, so plug in 3 pi over 4 first. These are all values on your pi plate. And you get 3 pi over 4 minus 1, which, if you use your calculator, is approximately 1.36. Now, just a reminder on our calculators, if this was a calculator question, I would like you to hit the math button and go to number 9 for the derivative and go from 0 to 3 pi over 4. 1 minus sine 2x. And remember, for all things, when we do derivatives, integrals, with trig functions, we want to make sure that our calculator is in radians. So my calculator is in radians here, so things are good that way. With regards to x, 1.85, did I type? Oh, I forgot the 2. With newer calculators, if you screw up like that, you know you can just highlight something so that it comes up again. And you have your insert button right here, so you don't have to retype everything. So hopefully you know those things already. There we go. 1.36. If you have an older calculator that doesn't let you go up and highlight something, you can also get previously written things by going second, and above the enter button is entry. Second entry pulls it up as well. Sometimes that's quicker if you just want to grab something right from before. So if you had your calculator for this, then I would be expecting you to go to that calculator because it's faster. And we want to become efficient, because when we get to our exam, right, Miss Murphy's room next door won't be available for extra time. We have a certain amount of time that we have to do it in. So we want to make sure that we're doing things as efficiently as possible. So now we want to find the distance traveled over the first 3 pi over 4 seconds. Here's the graph. And again, if we didn't have a calculator for this question, we would need to figure out where does your graph go into the negatives. How would you find that? You would have to solve where it's equal to 0. So solving where it equals to 0 without a calculator, I would get sine 2t equals 1/2. You know from your pi plate that sine is a half, positive a half, quadrant 1 and quadrant 2, at pi over 6 and 5 pi over 6. And because there is a 2t inside, that doesn't change the fact that it's still pi over 6 and 5 pi over 6. It just means that the 2t has to equal pi over 6 and 5 pi over 6. So then solving for t, divide each of those by 2, you get pi over 12 and 5 pi over 12. And if you didn't have your calculator, you would have to find the integral 3 separate times. From 0 to pi over 12, from pi over 12 to 5 pi over 12, and notice I already added absolute values around that because I knew it was negative at that section, so I would have to make that section positive. Sometimes you don't know which section is going to be negative until you do the calculations. And once you get your answers, you'd be like, oh, there's my negative part. That's the part I need to make positive. And I cheated here. I used a calculator, right? I would technically have to get this same integral. I'm going to just scroll up for a second here. I would technically have to use this same integral here and plug in all of those values from my pi plate to get my answers. But I cheated and used my calculator because I'm like, that seems like a lot of work right now. However, if you had your calculator and you wanted to get this 2.73, we're going to do that right now. Okay? And there is going to be something really important, a really easy mistake that's made is where do we put those absolute values? Okay? So we're going from 0 to 3 pi over 4. Our original function was 1 minus 2 sine 2t dt. And we have to add absolute value bars. So we have two options. I'm going to just actually... I'm going to show you the two options of where students put the absolute value bars. Option 1, they put the absolute value bars there. Option 2, they put the absolute value bars there. And one of two things happens. There are some students that say, it doesn't matter. The absolute value bars could be in either spot. It doesn't matter because I just need to make it positive. Okay? Then there are some students, nope, the first one is right. I better do the first one. And then there's some, nope, it's only the second. So think about it in this situation. Okay? What is happening here? Without the absolute value bars, we have displacement. So this part, if I just like move these away for a little bit, this part right now is the displacement. And the displacement says add up the positives and the negatives, combine it together, and find out how far away from your starting point you are. And it will give you an answer. So let's say this displacement, which we figured out in A, was 1.36. You are 1.36 away from where you started from. By putting the absolute value bars around the outside, which is wrong, you just make your displacement positive. It doesn't actually calculate your distance. So if we wanted to do our distance, we have to make sure that those absolute value bars are inside the function. That flips the function first, then you're adding all positive areas. Absolute values around the outside means add up your positives and negatives, and then whatever answer you get, make that positive. That doesn't tell you your distance. So now I'm going to go back to my calculator here. And we need to know, where do we find that absolute value symbol? So I'm going to go in here. I'm going to go back to the beginning. I'm going to see what happens. I don't think it's going to actually work, but I'm going to try to insert an absolute value. Now the absolute value is kind of hidden. It's under math. You hit the math button, but it's not listed as one of the math things. You have to go over to number, and it's listed. ABS stands for absolute value. So it's a little bit hard to find. And actually, when I inserted it, I'm going to have to rewrite the 1 minus 2 sign 2x. And delete the rest. And I get the 2.73 correctly right away from that. That is way faster than having to do all of that integration and figuring out. So make sure you're aware. If it's a calculator question, hey, I can go to my calculator and get this answer right away. Another thing I want to show you on your calculator, which might happen to you on your AP exam. You're like panicking. I don't know if that happens to you. You get a little bit nervous and you forget a little bit of something, and now you're like, stress level goes up and you're like, come on, I know, where's my absolute value? And you're hitting buttons all over the place on your calculator, and you're like getting frustrated. And unfortunately, you know, it's not something that I'm able to give you on the final exam. Where's my absolute value? I'm like, oh, here it is. And by the way, the multiple choice goes A, B, C, C, A. Just so you know. No, I can't say that on your exam, right? I can't give you answers or give you hints, but what I can do is, before your exam, give you as many tools as possible to help you. So, you can't find the absolute value because you've forgotten you have to hit math and then go over to number, right? And you're like, oh, I didn't know there was all these other things you could do, okay? But you remember that it looked like abs, because you thought of a really strong function with like a six-pack. So you were remembering that the absolute value was abs. All of the functions on this entire calculator are in a catalog. Above 0 it says catalog. So if you go second catalog, it lists everything. And it just so happens that it's alphabetical, that your abs show up first. So if you forgot where it was, it's nice that it shows up first. If you were like, oh, I want to find, I can't remember where n deriv was. Well, you remembered it was n deriv. So you can also go alpha, and if I go to n, it will take me, no, I don't have to push alpha. I just have to, let's start again. Catalog, because it's really annoying if you try to scroll all the way to n. But if I just hit n, it takes me to the end. Oh, there's n deriv right there. And I can push enter, and it enters it in for me, and it's ready to go. So if you forget where certain things are on your calculator, that catalog can be really, really helpful. Okay. All right, let us explain all of your physics formulas that you used to use and just use them because you were like, I have to use a formula. Now calculus can just explain it with SPA. So, a golf ball is thrown upward with a velocity of 7 meters per second from the edge of a cliff 75 meters high. How long will it take the golf ball to hit the ground? And you had formulas in physics where you could plug these in, and that's great. But It's even better if we know where these things come from and where the formulas come from and can understand them. So here's a picture. We've got some cliff here in blue. You're standing up here, or maybe you're sitting on the edge. That's dangerous. Shouldn't do that. And you're throwing a golf ball off of the cliff because it's just so much fun. What do we know? Okay. We know acceleration due to gravity is negative 9.8. So when we're thinking about SVA, we have the bottom given to us. We can work our way upwards. If I know my acceleration is negative 9.8, well then, and here are given conditions. We know our initial velocity. We know our initial displacement. So our velocity is just going to be the integral of our acceleration. And since it's a nice constant, that is really easy integral to figure out. So scrolling down here, I can calculate it. I get a plus C. This time I labeled it as C1 because I'm probably going to have a C2 later on. I would probably, I think if I was you, I would just go with C and then D. That's my, I think for me that's my favorite, but I mix it up a little bit here and there. So now since we know our initial velocity is 7, we can solve for C1, and now we have a velocity equation. Negative 9.8t plus 7. And our displacement is just the integral of our velocity. So if I want to find my displacement, because I'm wondering, what is the distance? This question said, how far has it traveled? So in this case, I'm going to need to get my displacement formula easy again to integrate. And I did put a C2. Should we change them to C's and D's? No, we've already written down C2. And we plug in 0 for time. Since we knew our initial displacement was 75, we now have that C2 is 75. And so we've used calculus to come up with our displacement equation. Yes, your physics formulas do this as well, right? What's the problem with formulas is that if you don't have them memorized, they're not very useful. Now, how long will it take for the golf ball to hit the ground? Well, based on our diagram, what do we know when it hits the ground? It's 75 below where it started from, right? Because the cliff was 75 high. So we would know we could plug in 0 for the displacement, because it would need to be on the ground. Our initial displacement was 75 meters above the ground. And when we solve this with our graphing calculator, we get 2 times, but one of the times is negative. And in the context of the question, you're sort of like, yeah, the ball hit the ground 3.2 seconds before I threw it in the imaginary past. That doesn't make much sense. So then the only one that is possible is the positive value. Now, if you have formulas, like in your physics classes, sure, it might be a little bit faster because you could just plug things into certain formulas and get your answers. That is also the beauty of formulas and why they're so useful. But it's nice to see right from just ideas of calculus why this works. Okay, let's go to a little bit more complicated one. Nathan designed a car, right? Poor Nathan. He designed this car. He probably was thinking, if it sped up steadily from 0 to 100, that might be the best fuel efficiency possible. And he's going to be like, going to introduce this as an option on cars to help reduce their gas, and what comes along? Electric vehicles. Totally ruins all of his research. Because, yeah, the electric vehicles are like, yeah, we don't use any gas. Doesn't matter how we accelerate. So he's like, oh, crap. Anyways. But he's doing his research anyways, and one day he set out on the highway and reached his cruising speed from 0 to 100 in exactly 20 seconds. How far did he go? And I like this question initially because it just seems like you're not given enough information. And you look at it and go, oh, that is a good question, but I don't feel like I could answer it. Okay? So we have to break things down. What do we know? Okay? We know that we have times of 20 and times of 0. We know that the acceleration is constant. So I'm going to introduce you to a nice new Greek letter. Does anybody know what Greek letter this is? Lambda. Oh, it's a fun Greek letter. Why not? I could use K. We should. You have issues with lambda? Go ahead. Make it K. Might make you feel like you can't solve this question because it's a new Greek letter you've never seen before. But if your brain is able to work with something new, that's good to expand. Okay. So we have a constant. We know that our acceleration is constant. We also have some issues here with units. We've got speeds in kilometers per hour. We've got a question asking for how far did he go in meters in the first 20 seconds. So this is a units nightmare to begin with because you've got some things wanting kilometers per hour, some things meters per second, some things in seconds, some things in meters. So we need to convert so we're all using the same unit. So the first thing I'm going to do is I'm going to take my 100 kilometers per hour and I'm going to convert that to meters per second. You get 250 divided by 9. If you're wondering how you do that, 100 kilometers in 1 hour, well, you can multiply that by 1,000 to get 100,000 meters in 1 hour. Okay? Then 100,000 meters in 1 hour means that you've got 100,000 meters in 60 minutes. So you could divide by 60, and then you would have how many meters per minute that you're going. And then in each minute, there's another 60 seconds, so you have to divide by 60 again. So we get that we're going 27 7/9, or 250 over 9 meters per second. Similarly, we could do that complex conversion to calculate that 0 kilometers per hour is actually 0 meters per second. I hope you do all that dividing and multiplying all the way through to calculate that. Some people, amazingly, I don't know how they do this right in their head. Okay, so there's our preliminary stuff. And since acceleration is constant, well, we can integrate to go backwards. So our velocity will be the integral of lambda dt. This is where you might really like k. It might throw you off if we use lambda. Right? It would just be kt, or lambda t, plus c1. And plugging in our initial condition, we know that when time is 0, velocity is 0. We get that our velocity equation is just lambda times t. But we also know that at time 20, Our velocity is 250 over 9. And you see, we now have enough information to solve for lambda. We could plug in the 20 for t, the 250 over 9 for the velocity, and now we can solve and figure out that lambda is 25 over 8, which in turn lets us find the exact velocity equation. So because we were given two pieces of information about the velocity, that allowed us to solve for lambda. Now our displacement, relatively simple. We just have to integrate here, add 1 to the exponent, and divide. It took 20 seconds. So we wanted to find out how far did it travel in those first 20 seconds. Now we can plug in 20 for t. Oh, let's do this. Maybe I had that in this box. Yeah. So you could do plus d. And this time when t is 0, you haven't traveled anywhere, the displacement is 0, so d would be 0. Now we can plug in that 20, and we can find out that in the first 20 seconds, you would go from 0 to 100 kilometers per hour in 277.8 meters. Next time you're in your car, visualize, can you visualize 277 meters? Did you ever have to run track and field? Did you ever run 100 meters? You have to imagine like 3 of those races. Get that distance, and you're at a stop sign. Get that distance in the futures, kind of mark it out, and then hit accelerate and see if you can get to 100 kilometers. Does it take you this long? 20 seconds to get to 100 kilometers is pretty small, actually, right? What are the fastest? Are there any car fanatics in here? Like it can get from 0 to 60 in. What are some times that you've heard of fast cars? No car fanatics. And now we can connect to the idea of the average of a function that we were doing before. Remember, the average of a function was 1 over the distance you were looking at, and then the integral over that distance. And we calculated average, like calculating average velocity. You've done this before without integrals. You're still able to. Do not lose the knowledge that you have from earlier. If it takes me 2 hours to drive 100 kilometers, what is my average speed? 50 kilometers per hour. We're ahead of the other class. Would you like to see an interesting video? We'll talk about these and I'll show you the video and we will go from there. So average velocity, you already know it's however far you traveled divided by the time that it took. So we could do S of B minus S of A over B minus A. And it just so happens that this is also equal to the average of a function, which is the integral from A to B of V of t. And if you think about, right, integrating this is just s of t in square brackets from b to a. Can you see that that is exactly s of b minus s of a? So what you already knew for average velocity, now it shows up also in our integration formula, which is super cool. If you wanted to find average speed, right, now we need to make sure that we have our absolute values in there. So this is a different thing than finding average velocity. Okay? Notice that when people are talking about these things, when they're actually driving, people always find average velocity. They just figure out how far they went and how long it took them. They don't actually figure out their average speed because sometimes you like drive backwards, forwards, your road is winding, right? We're not actually finding an average speed, but in conversation, someone will say, well, my average speed was this. So just interesting to notice that difference. And then we can also do this with average acceleration. So we'll do some of those questions tomorrow.